Hey guys, so right now we're starting section 5.4, sampling distributions, which is one part of this section, and then the central limit theorem, which does apply directly, but we have to learn what sampling distributions actually means. So before, when we were dealing with a normal bell curve, we found throughout the whole entire population, as long as it was normally distributed, we had a central value that was our mean, and our standard deviations, after doing a ton of really annoying math, would be found to be a certain distance away from the mean, okay? Now, that distance, the bigger the population got, the bigger the distance got. So when we talk about a sampling distribution, what we do with a sampling distribution is take a whole population and then split it into groups. Like, say, we could have groups of n equals 2 or n equals 5. Or if we have, say, 100 people, we might group them into, say, groups of n equals 10 people per group. And then within that smaller sample of the population, we can then find the mean. And when we do that, and then continue with the variance in the standard deviation, what we see is that we will get a normal distribution curve, which is a lot taller, but because we've taken smaller samples, our standard deviations are going to be closer to the mean than they were if we didn't take smaller groups of that population. And the reason that the curve, when you take a sampling distribution and set it up into a bell curve, the reason that that bell curve is so much taller is because the area under this curve always has to equal 100%. Or as a decimal, it would be 1, okay? So obviously, if you squish together the standard deviations and make them closer together, therefore closer to the mean, that area has to be absorbed by making the curve stand up higher, okay? The mean will still be the same, but the standard deviations would be smaller, and the variance would be smaller as well, okay? So that's what we're looking at today, is to how to get more specific information from our bell curve, okay? So we will have another set of equations or formulas that go along with variance and standard deviation. The mean for both a sampling distribution and the population distribution, that mean is the same for both, okay? That's the only thing that's the same. The other things that we would find, the variance and the standard deviation, those are different, and I will provide you with the best method to get through the problems. So the formulas for the sampling distribution, the mean is the same, and those are on the bottom of page 261, okay? You've got the mean is the same, and in order to represent the sampling distribution, we use that notation. That little X bar, this thing right here, that's called X bar. That means that we are finding the mean of the sampling distribution, okay? But that is the same as the mean of the regular population. Okay, and then number 2 down there in that box give us the formula for standard deviation as far as sampling distribution goes. And when I worked through these initially, I found that I struggled greatly with just those 2 formulas, okay? So what we're going to do is, as we work through the first example using a sampling distribution, I'm going to give you the best way to work through these problems, okay? The only way that I could make it make sense. Okay, so what we are going to do is we're going, instead of, you'll see why we're not going to do try it yourself 1 with this particular example 1, because as we work through the given example, and I'm going to show you how to do it, you'll understand why it is a very tedious process. Anyway, let's get to it. Okay. So what we need to make note of here, it says you write the population values on slips of paper. So 1, 3, 5, and 7. And you could, for all intents and purposes, call that your domain, okay? That is something that we definitely need to make note of. So I'm going to write population, and I will call that domain if I need to refer to it verbally as I'm making this video for you guys, so you know exactly what values I'm talking about, okay? So we have that population, 1, 3, 5, 7, and it says you put those slips of paper in a box. Then you randomly choose 2 slips of paper with replacement. So that 2 is going to be our n value, okay? N equals 2. Okay, list all the possible samples of size n equals 2 and calculate the mean of each. Okay, this is where things get a little bit tedious, and you have to be really, really careful that you don't miss anything. Okay, so for right now, we'll have the samples. So if we're picking 2 of those numbers with replacement, that means that at any time, any of those can be repeated. So what we're going to do is list all the possibilities of picking 2 of those numbers. Okay? Now, from our previous sections here in probability, if we've got 4 numbers, 1, 3, 5, and 7, and we are picking with replacement 2 of them, we know that for each 2, we have 4 choices. So 2 times 2 times 2 times 2 means that we better come up with 16 different samples here. Okay, and we will. Okay, so I started with the 1, and I paired 1 with 1, then 1 with 3 because that was the next number, then 1 with 5, then 1 with 7, and then I went to the next number in line, which was 3. And I paired that with each number, moved on to the 5, the 7, etc. And I'm almost done. Okay, and I am squished down here at the bottom, but this is the last number. Okay, so those are the samples. Okay, now the next column that we will have is going to be, let me erase that and move it over a little bit. Here we go, so we can separate everything nicely. The next section, in order to keep track of all of this seemingly randomness, is going to be the sample mean. Okay, so what that means is that within each set of parentheses, you're going to add those 2 numbers together and divide it by the number of numbers you've got, which is 2. So 1 plus 1 is 1. Been a long time since I've been in class, guys. 1 plus 1 is 2, divided by 2 is 1. And we'll do the same thing. 1 plus 3 is 4, divided by 2. So all of these numbers then are very easy to come up with. You don't, at this point, for some of them, you'd need your calculator because they may get quite big. But here, they are very easily determined in your head, okay? So half of 6 is 3, half of 8 is 4, half of 10 is 5, half of 12 is 6, and then 4, and then 5, and then 6, and then 7. Okay, so that's the sample mean. Now the next column is going to be the possible, that's what that POSS stands for, abbreviated possible sample means, okay? In this column, we're going to take one of each one of those numbers in the sample mean column. So we've got a 1, a 2, a 3, a 4, and I'm going to go down the list here, and I see I've got a 5, and I'm going to keep going down the list here, and I've got a 6 and a 7. Okay, so those are all of the different possible sample means, and I only need one of each. Okay, and then in the next column, we are going to find the frequency. Okay. Okay, so how many ones do I have? It looks like when I go down that list of sample means, I've only got 1 1. And when I go down the list, I'll see I've got 2 2s, I've got 3 3s, and that is just coincidental. I've got 4 4s. Boy, that's squished. Let me spread that out a little bit. I've got 3 3s, 4 4s, 3 5s, 2 6s, and 1 7. Okay, and then they have us finding the probability, although if we don't have the probability from the normal population, we don't really have much to compare this with, okay? But to find the probability values, the frequency divided by the number of samples you've got, which is 16. So 1 divided by 16, and then you get your probability values here, okay? So then 2 divided by 16, so I'm just going to write these down here because you will have to complete a whole entire table. And then 0.25. So what this would tell us is that because we are taking samples from a bigger population, a smaller number of parts per se of that population, we've got a probability then that will be more accurate, okay? That may possibly be more accurate than the probability of a large population that you're not splitting into smaller groups, okay? When you've got smaller groups, you're able to more accurately pinpoint exactly the mean, the variance, and the standard deviation, okay? And then you can put all those samples together to create your sampling distribution, which is what we're doing right now. Okay, so from this point, what we're doing now is finding population facts, okay? And you need your population facts in order to determine your sample facts, which is what we are actually after, okay? So the population facts. Now, the population is that domain of numbers in that set of pretty squiggly brackets there, okay? So the population facts, the mean is to add those 4 numbers together, 1 plus 3 plus 5 plus 7, and divide by the number of numbers that you've got, which is 4. So that gives you that your mean, if you add up all those numbers, you get 16 over 4, which is 4. Now, to find your standard deviation of the population, you're going to take 1 minus 4 and just add all of the sum of the squares, the difference of the value and the mean, and then square them. So we have 1 in our population, so 1 minus the mean squared, then 3 minus 4 squared, then 5, and then 7. Okay. And all of that is also over the number of, I want to say, numbers you've got within your sets of parentheses. So you've got 4 sets of parentheses up there. So that n value there is a 4. Okay, so 1 minus 4 is negative 3 squared is 3. 3 minus 4 is negative 1. Negative 1 squared is a positive 1. 5 minus 4 is 1 squared, which is 1. And, wait, that 3 should be a 9. Sorry, hold on, guys. 1 minus 4 is negative 3 squared is 9, not 3. Okay, and then 7 minus 4 is 3 squared, which is also not 3. Okay, over 4. So you have 10 and 10, 20 divided by 4. So what we're going to do is leave that as a 20 divided by 4. So I'm just going to, because, and I'll show you why, just because it might make other problems like this easier, although we do know that 20 divided by 4 is 5. So, and then that is our variance, okay? Now we can find the standard deviation by taking the square root of 5, because that's actually variance, not standard deviation. So the variance is 5, and then the standard deviation would be the square root of that. So let's find that quick, okay? The standard deviation is the square root of 5, which is 2.2. 2.24. That's the standard deviation when the variance is 5. Now we're going to utilize some of that information to come up with our sample facts, okay? Because what we're being asked to find in example 1 is find the mean, variance, and standard deviation of the sample means. So we're using the population facts to find the sample facts. So the mean is the same, okay? The mean of the sample is equal to the same mean as the population. So that's 4. Now, in order to find variance of the sample, okay, so we're going to use our correct notation here. To find the variance of the sample, we would take that 20 over 4, the variance from the population. And for this particular case, we can use the 5 because it divided evenly. But if it did not divide evenly, you'd want to keep it as a fraction. So that number 5 for the variance in the sample comes from the variance in the population. And then we put that over the n that we've got, which if you look up at the top, our n is equal to 2 because we were taking those domain values and grouping them in groups of 2. So the variance is 5 over 2. Therefore, the standard deviation is the square root of that. Now the square root of 5 over 2, which is 2.5, is 1.6. Okay, so as you can see, our mean is the same for both. The mean is 4 for both the population and the sample. So the mean is 4. If you notice in the population, our standard deviation is 2.24, while in the sample, it's only 1.6. So again, that's why when you look at a sample graph, the normal distribution, you've got the mean in the middle, but all the standard deviations are closer to the mean, which not only changes the shape of the graph, it also gives us more accurate readings. Okay, so we've got a smaller variation, therefore a smaller standard deviation. Okay, so again, you can see why, even though we've got 4 numbers in our population, 1, 3, 5, 7, we're only grouping them in groups of 2. The try it yourself 1, we've got only 3 values in our domain, but we are grouping them in groups of 3. And when we do that, we come up with 27, which just, I don't even have enough room on my board here to get that all put together without having to make 2 columns, which makes it very messy. Okay, so this is the way that you will do problems that involve finding the variation and standard deviation of a sample distribution, okay? I recommend doing it exactly this way, because if you try to do it by the way the book has it, you will get lost, okay? It took me quite a while to make some sense out of how they were doing it and making it easier to understand for us. Okay, so that was from example 1, okay? Now, when we look on page 263, we're looking down at the bottom of that page, okay? Okay, so right now we're looking down at the bottom of page 263, and my recording did pause at some point that I don't know, but I don't think it was more than for a second or two. So anyway, we're on the bottom of page 263, and the central limit theorem is very similar to what we've been doing, and we'll show that in application as we go through the examples, and of course I will provide you with the formulas that you need and how to use them. But on the bottom of page 263, you can see you've got any population distribution, which really crazy shaped right under the number 1, okay? And then all the other ones are normal distribution, okay? Look at, in column number 2, you've got 2 curves, okay? And this is very important because there is some homework that is related to this particular concept, okay? We're in column 2. Notice you've got your mean, and in the top drawing, okay, your standard deviations are spread out a little farther than the one in the drawing underneath, because the one on the top is from a population, and the one here on the bottom is from a sample, okay? The sample means what's important to realize is that if the information used for both these curves is coming from the same set of data, the mean is going to be the same. So the mean is the same and the standard deviation for the bottom curve here is smaller. Okay, and again, that's imperative to know because that is going to be one of the questions that you'll find in your homework, that you understand the difference, okay? The area under the curves still has to be 100%. But if you're squishing all your information together, that just means that you're making the curve taller. The mean doesn't change. The standard deviation does, and it will be smaller, okay? Now, we're looking at example 3, which is a central limit theorem, okay, which kind of gives us the same information, but we can utilize math for this, okay? So we have a random sample. We're looking at try it yourself 2 on the bottom, okay? We have random samples of size 64 are drawn from the population in example 2. And when you look in example 2, we are told that the mean, which will be the same as the sample mean, is $47, okay? And I'm just drawing from the information given in example 2, okay? It also says then that the standard deviation is $9, okay, for population. Now, what we're doing is we are going to apply that information in Try It Yourself 2. But this time we've got an N of 64, where in example 2, they had an N of 100. It says random samples of 100 cell phone bills. Here we're using 64. So the first thing we're doing in Try It Yourself 2 is finding the mean. So Try It Yourself 2A, it says find the mean of the sample. Well, that is going to be the same. Remember, it's always the same. But what we need to do is find the standard deviation, okay? So in order to find the standard deviation, that formula is the standard deviation from the above information all over the square root of n, which in our case is 64. So the square root of 64 is 8, okay? So when you do that division, you get 1.125 as your standard deviation for the mean, okay? So we can actually create a curve from that. Okay, our mean is right there in the middle. Okay. And how we get to these standard deviations is to add 1.12, it should be 1.125, to 47. So 47.125 here would give us 48.125. Then we would add 1.125 to that and get 49.25, etc. Then we would subtract the standard deviation from 47, and this value right here would be 45.82 or 875. And then subtract 1.125 from that to get the next value, etc. Okay? So that's just what it would look like. Okay? That is what it would look like with your sample mean. And the formula for finding the standard deviation, if you recall from this mess here, we took for the sample fact, we took, I'm going to try to change colors and see if it, we took this value right here of 5 from the variance in our population. Okay? Then, of course, then you take the square root of all of that to get your standard deviation. This time they gave us our standard deviation. Okay? All right. So next we are looking at example 3, and we've got try it yourself 3. Okay? So let's just look at the graph here. The graph that we're given looks something like that, and that's obviously very skewed. Okay? And you've got a mean of 3.5, and then your first standard deviation is at 3.7, then 3.9, and obviously from that we can see that the standard deviation is 0.2. Okay? Now, if we were to take the sample, we're going to find that our standard deviation is quite a bit smaller. Okay? The standard deviation from this graph is 0.2 because 3.7 minus 3.5 gives us a difference of 0.2. If we were to do that for the sample, the formula for the sample to find the standard deviation is to take the standard deviation from the population and divide it by the square root of n. Okay? So our standard deviation is 0.2. The mean is still 3.5, but we've got random samples of size 16. Okay, so that means in order to find the standard deviation of the sample, we take the standard deviation from the population, which was 0.2, and our random sample of 16 has a square root of 4. So when we use the sample, we come up with a standard deviation of 0.05, which 0.05 is definitely less than the standard deviation of the population, which is 0.2. Okay, so the graph then would have the same mean right here in the middle of 3.5, but the next standard deviation would be 0.05 greater than that. So it would be 3.55. Okay, and then we'd add 0.05 to get the next standard deviation. And then going to the left of the mean, 3.5 minus 0.05 would give us our first standard deviation to the left at 3.45. Okay, and again, same mean, smaller standard deviation. That's what the central limit theorem tells us. The closer together you've got the standard deviation to the mean, the higher the graph is with the same mean, but your information is more targeted to smaller groups. Okay, and just as I feared, looking at the time that this video has taken pretty much takes up all of our class time. Because if I started on the next example, I wouldn't be able to finish probably even that example, much less the rest of the section. So that will be reserved for next week. Okay, see you guys. To be continued.